Definition: organic farming is an agricultural approach that emphasizes sustainable and holistic practices, avoiding synthetic chemicals and genetically modified organisms. It relies on natural processes, biodiversity, and ecological balance to enhance soil fertility and produce healthy crops. 2. Concept of organic farming. Key principles: soil health, emphasis on building and maintaining healthy soil through organic matter, cover cropping, and reduced tillage. Biodiversity, encourages diverse crop rotations, intercropping, and the preservation of natural habitats to support a range of beneficial organisms. Avoidance of synthetic inputs, excludes synthetic pesticides, herbicides, and fertilizers, instead, relies on natural alternatives. Animal welfare, emphasizes the humane treatment of animals, with organic livestock raised on organic feed without routine use of antibiotics or growth hormones. 3. Relevance in the present context. A. Environmental sustainability. Reduced chemical inputs. Organic farming minimizes the use of synthetic chemicals, reducing environmental pollution and preserving biodiversity. Soil conservation, emphasis on soil health and conservation practices, helps prevent soil erosion and degradation. B. Health and nutrition. Nutrient-rich crops. Organic farming methods often result in crops with higher nutritional content. Avoidance of residue, absence of synthetic pesticides reduces the risk of chemical residues in food, contributing to food safety. C. Consumer demand. Growing market. There is a rising consumer demand for organic products due to health and environmental concerns. Certification standards. The establishment of organic certification standards ensures transparency and authenticity in organic produce. D. Climate change mitigation. Carbon sequestration. Organic farming practices, such as cover cropping and reduced tillage, contribute to carbon sequestration in the soil. Resilience. Organic systems are often more resilient to extreme weather events, supporting climate change adaptation. E. Economic viability. Market opportunities. Organic farming provides opportunities for farmers to access premium markets and differentiate their products. Reduced input costs. Over time, organic farming may lead to reduced input costs as reliance on external inputs decreases. F. Sustainable agriculture. Long-term viability. Organic farming aligns with the principles of sustainability, focusing on long-term viability and resilience of agricultural systems. Cyclical systems. The closed-loop systems of organic farming reduce dependence on external inputs. G. Soil and water conservation. Water efficiency. Organic farming practices, such as mulching and cover cropping, contribute to water conservation and efficient use. Reduced water contamination. Avoidance of synthetic chemicals helps prevent water pollution. H. Social and ethical considerations. Fair trade practices. Some organic farming initiatives incorporate fair trade principles, ensuring fair wages and ethical treatment of workers. Community development. Organic farming can contribute to community development by promoting local, sustainable agriculture. In summary, organic farming is gaining relevance in the present context due to its alignment with environmental sustainability, health and nutrition, consumer demand, climate change mitigation, economic viability, and social and ethical considerations. As the global agricultural landscape evolves, the principles of organic farming offer a compelling model for addressing contemporary challenges and promoting a more sustainable and resilient food system. U. Organic production requirement. Organic production involves growing crops or raising livestock using methods that avoid synthetic pesticides, fertilizers, genetically modified organisms, GMOs, and other artificial inputs. The goal is to promote ecological balance, conserve biodiversity, and produce food in an environmentally sustainable and socially responsible manner. Organic production standards are established and regulated to ensure the authenticity of organic products. The specific requirements for organic production can vary by country or region, but they generally share common principles. Here are key aspects of organic production requirements. 1. Soil management. Prohibition of synthetic chemicals. Organic production prohibits the use of synthetic fertilizers, pesticides, herbicides, and other chemicals. Soil fertility. Emphasis on building and maintaining soil fertility through the use of organic matter, compost, cover crops, and crop rotations. Avoidance of GMOs. Organic standards typically prohibit the use of genetically modified organisms in seeds or crops. 2. Crop management. Seed selection. Use of organic seeds is encouraged, and the use of genetically modified seeds is prohibited. Crop rotation. Implementation of crop rotation practices to manage pests, diseases, and soil fertility. Companion planting. Utilization of companion planting to enhance biodiversity and control pests naturally. 3. Pest and disease management. Prevention strategies. Emphasis on preventive measures, such as crop rotation, companion planting, and habitat management, to minimize pest and disease issues. Organic pest control. Use of natural predators, beneficial insects, and non-synthetic methods for pest control. Prohibition of synthetic pesticides. Avoidance of synthetic pesticides and herbicides. 4. Livestock management. For organic livestock production. Organic feed. Livestock must be provided with organic feed that is free from synthetic additives and GMOs. Access to outdoors. Livestock must have access to the outdoors and be provided with living conditions that allow for natural behaviors. Prohibition of growth hormones and antibiotics. The use of growth hormones and routine antibiotics is prohibited. 5. Handling and processing. Segregation. Organic products must be segregated from conventional products during handling and processing. Prohibition of synthetic additives, use of synthetic preservatives, colors, flavors, and other additives is restricted. Organic certification. Farms and processing facilities must undergo organic certification by a recognized certification body to verify compliance with organic standards. 6. Record keeping and documentation. Traceability. Maintain detailed records of all activities, inputs, and transactions related to organic production. Documentation for certification. Provide necessary documentation for organic certification, demonstrating compliance with organic standards. 7. Inspection and certification. Third-party certification. Organic farms and processing facilities are typically subject to regular inspections by third-party certifying agencies to ensure compliance with organic standards. Certification process. Obtain and maintain organic certification from an accredited certification body. 8. Labeling and marketing. Use of organic label. Only products that meet organic standards can carry the organic label. Marketing claims. Accurate representation of organic products in marketing materials, adhering to regulations on organic claims. Adherence to these requirements is essential for maintaining the integrity of organic production and ensuring that consumers can trust the authenticity of organic products. Certification bodies play a crucial role in verifying compliance with organic standards through regular inspections and audits. Biological intensive nutrient management. Biological intensive nutrient management. Biological intensive nutrient management, BINM, is an agricultural approach that emphasizes the use of biological processes and interactions to manage nutrients in a sustainable and efficient manner. This method seeks to enhance soil fertility, optimize nutrient cycling, and promote plant health by harnessing the power of biological organisms, such as microbes and plants. Here are key aspects of biological intensive nutrient management. 1. Soil microbial activity. Microbial inoculants, application of beneficial microorganisms, such as mycorrhizal fungi, rhizobacteria, and other soil microbes, to enhance nutrient availability to plants. Microbial diversity, promoting a diverse microbial community in the soil, which contributes to nutrient cycling and soil health. Composting, using microbial decomposition through composting to convert organic matter into nutrient-rich humus. 2. Cover crops and green manure. Cover crops, planting specific crops during fallow periods to cover the soil, prevent erosion, and add organic matter. Green manure, incorporating plants into the soil while they are still green to improve soil structure and nutrient content. 3. Crop rotation and polyculture. Crop rotation, alternating the types of crops grown in a specific field over different seasons to disrupt pest cycles, enhance soil fertility, and manage nutrient demands. Polyculture, growing multiple crops in the same field simultaneously, promoting biodiversity and reducing nutrient imbalances. 4. Nutrient cycling and recycling. Organic residues, recycling organic residues such as crop residues and animal manure to return nutrients to the soil. Nutrient mining, avoiding excessive nutrient mining by ensuring that nutrient removal by crops is balanced with nutrient replenishment. 5. Biofertilizers. Rhizobium and nitrogen-fixing bacteria, inoculating leguminous crops with nitrogen-fixing bacteria to enhance nitrogen availability. Phosphorus-solubilizing bacteria, using bacteria to solubilize phosphorus in the soil and make it available to plants. 6. Vermicomposting. Use of earthworms, utilizing earthworms to break down organic matter in a controlled environment, resulting in nutrient-rich vermicompost. 7. Organic amendments. Compost and humic substances, applying compost and humic substances to improve soil structure, water retention, and nutrient availability. Biochar, incorporating biochar into the soil to enhance nutrient retention and improve microbial activity. 8. Precision agriculture. Site-specific nutrient management, utilizing precision agriculture technologies to tailor nutrient inputs based on specific soil and crop conditions. Sensor-based monitoring, employing sensors to monitor nutrient levels in real time and optimize nutrient application. 9. Agroforestry. Integration of trees, incorporating trees into agricultural systems to improve nutrient cycling, provide shade, and contribute organic matter. 10. Farmer training and education. Knowledge transfer, providing farmers with training and education on the principles and practices of biological intensive nutrient management. Skill development, empowering farmers with the skills needed to implement sustainable nutrient management practices. Biological intensive nutrient management promotes a holistic and ecologically sound approach to nutrient management, aiming to create a balanced and self-sustaining agroecosystem. This method enhances the biological activity in the soil, improves nutrient availability to plants, and contributes to long-term soil fertility and productivity. Recycling of organic residues, biofertilizers. Recycling of organic residues. Recycling organic residues is a sustainable agricultural practice that involves reusing organic materials, such as crop residues, animal manure, and other plant and animal byproducts, to enhance soil fertility, improve soil structure, and promote overall agroecosystem health. Here are key aspects of the recycling of organic residues. 1. Crop residues. Harvest residues, incorporating crop residues back into the soil after harvest. Mulching, using crop residues as mulch to reduce soil erosion, conserve moisture, and suppress weeds. Green manure, growing cover crops and incorporating them into the soil while green to add organic matter and nutrients. 2. Animal manure, manure application, applying animal manure to fields as a source of organic matter and essential nutrients. Composting, composting animal manure to enhance nutrient availability, reduce pathogens, and improve soil structure. 3. Food waste and composting, composting food waste, composting kitchen scraps and food waste to create nutrient-rich compost. Urban agriculture, utilizing composted organic waste in urban agriculture and community gardens. 4. Bioenergy production, anaerobic digestion, using anaerobic digestion to convert organic residues into biogas for energy production. Biofuel production, using certain organic residues for biofuel production, contributing to renewable energy sources. 5. Integrated systems, agroforestry, integrating trees into agricultural systems to recycle organic residues, improve nutrient cycling, and provide additional organic matter. Cover cropping, planting cover crops to capture and recycle nutrients, prevent soil erosion, and enhance soil fertility. Biofertilizers. Biofertilizers are biological products containing living microorganisms that enhance nutrient availability and uptake by plants. They contribute to sustainable agriculture by improving soil fertility, promoting plant growth, and reducing the dependence on chemical fertilizers. Here are common types of biofertilizers. 1. Nitrogen-fixing bacteria, Rhizobium. Legume symbiosis, forming symbiotic relationships with leguminous plants to fix atmospheric nitrogen into a form that plants can use. Enhanced nitrogen availability, improving nitrogen availability in the soil for non-leguminous crops. 2. Phosphorus-solubilizing bacteria, phosphate solubilization, converting insoluble phosphorus in the soil into a soluble form that plants can absorb. Improved phosphorus uptake, enhancing phosphorus uptake by plants, promoting root development and overall growth. 3. Mycorrhizal fungi, symbiotic relationships, forming symbiotic associations with plant roots to enhance nutrient absorption, particularly phosphorus, and other micronutrients. Improved nutrient and water uptake, facilitating improved nutrient and water uptake by plants. 4. Azotobacter and azospirillum, nitrogen fixation, contributing to nitrogen fixation and nutrient cycling in the rhizosphere. Promoting plant growth, producing growth-promoting substances that benefit plant development. 5. Cyanobacteria, blue-green algae nitrogen fixation, fixing atmospheric nitrogen and releasing it into the soil. Biofertilizer application, used in rice fields and other crops to enhance nitrogen availability. 6. Application methods, seed inoculation, coating seeds with biofertilizer inoculants before planting. Soil application, direct application to the soil around plant roots. 7. Benefits, reduced chemical dependency, biofertilizers reduce the need for synthetic fertilizers. Improved soil health, enhancing soil microbial activity and biodiversity. Sustainable agriculture, contributing to sustainable and environmentally friendly agricultural practices. Both the recycling of organic residues and the use of biofertilizers are integral components of sustainable agriculture, promoting nutrient cycling, improving soil fertility, and reducing environmental impacts associated with conventional agricultural practices. Use soil improvement and amendments. Soil improvement and amendments. Soil improvement involves enhancing the physical, chemical, and biological properties of soil to create a more favorable environment for plant growth. Various soil amendments are used to address specific soil deficiencies or imbalances. Here are common soil improvement practices and amendments. 1. Organic matter addition. Purpose: organic matter improves soil structure, water retention, and nutrient availability. Amendments: compost, decomposed organic material rich in nutrients. Manure: animal waste that contributes organic matter and nutrients. Cover crops for green manure, plants grown and incorporated into the soil to add organic matter. 2. Mulching. Purpose: mulching conserves soil moisture, regulates temperature, suppresses weeds, and adds organic matter. Amendments: straw, hay, or wood chips, common mulching materials. Cover crop residues, left on the soil surface as a mulch after cover crops are terminated. 3. Lime application. Purpose: raises soil pH, making it less acidic and more suitable for a wider range of crops. Amendments: agricultural lime, contains calcium carbonate or calcium magnesium carbonate. Dolomite lime, contains magnesium carbonate in addition to calcium carbonate. 4. Gypsum application. Purpose: improve soil structure and drainage in clay soils without significantly altering pH. Amendments: gypsum, contains calcium and sulfur. 5. Nitrogen-fixing cover crops. Purpose: enhances nitrogen availability in the soil through biological nitrogen fixation. Amendments: leguminous cover crops, examples include clover, vetch, and peas. 6. Phosphorus and potassium amendments. Purpose: addresses deficiencies of phosphorus and potassium, essential nutrients for plant growth. Amendments: rock phosphate, a natural source of phosphorus. Potash, a source of potassium. 7. Micronutrient amendments. Purpose: corrects deficiencies of essential micronutrients like iron, zinc, manganese, and copper. Amendments: chelated micronutrients, forms that enhance micronutrient availability. 8. Biochar application. Purpose: improve soil structure, water retention, and nutrient availability while sequestering carbon. Amendments: biochar, charcoal-like material produced from the pyrolysis of organic matter. 9. Vermicomposting. Purpose: converts organic waste into nutrient-rich vermicompost through earthworm activity. Amendments: vermicompost, compost produced by earthworms. 10. Sulfur application. Purpose: corrects sulfur deficiencies in the soil and contributes to the synthesis of certain amino acids. Amendments: elemental sulfur, converted to sulfuric acid by soil bacteria. 11. Green sand. Purpose: provides potassium, iron, and other minerals, improves soil structure. Amendments: glauconite, a greenish mineral containing various essential nutrients. 12. Cover cropping and crop rotation. Purpose: enhances soil structure, suppresses weeds, and improves nutrient cycling. Amendments: leguminous cover crops, fix nitrogen and improve soil fertility. Diverse crop rotations, break pest cycles and promote soil health. 13. Mycorrhizal inoculants. Purpose: enhances the symbiotic relationship between plants and mycorrhizal fungi for improved nutrient uptake. Amendments: mycorrhizal inoculants, contains beneficial mycorrhizal fungi. 14. Sulfur and compost teas. Purpose: provides nutrients and enhances microbial activity in the soil. Amendments: sulfur tea, extracts nutrients from sulfur-containing materials. Compost tea, microbe-rich liquid extracted from compost. 15. Biofertilizers. Purpose: introduces beneficial microorganisms to the soil for improved nutrient cycling and availability. Amendments: rhizobium and mycorrhizal inoculants, enhance nitrogen fixation and nutrient absorption. Soil improvement and amendments are integral to sustainable agriculture, promoting healthy soil ecosystems, optimizing nutrient availability, and fostering optimal conditions for plant growth. The choice of amendments depends on specific soil characteristics, nutrient deficiencies, and crop requirements. Regular soil testing is essential for informed decision-making regarding the selection and application of soil amendments. U. Integrated diseases and pest management, quality considerations, certification, labeling and accreditation processes, marketing, exports. Integrated disease and pest management, IDPM. Integrated disease and pest management is an approach that combines various strategies to control diseases and pests in agriculture in a sustainable and environmentally friendly manner. The goal is to minimize the use of chemical inputs and promote ecological balance. Here are key components of IDPM. 1. Biological control, use of natural predators, introducing or encouraging natural predators, parasites, or pathogens to control pest populations. Conservation of beneficial insects, implementing practices that support beneficial insects. 2. Cultural practices, crop rotation, alternating the types of crops planted to disrupt pest and disease life cycles. Polyculture, growing different crops together to reduce pest and disease susceptibility. 3. Mechanical and physical controls, traps and barriers, using physical barriers or traps to prevent pest access or capture them. Cultivation practices, employing practices like plowing to disrupt pest life stages. 4. Chemical control, as a last resort selective pesticide use, targeting specific pests with minimal impact on non-target organisms. Integrated pest management, IPM, applying pesticides judiciously based on monitoring and economic thresholds. 5. Disease-resistant varieties, breeding for resistance, developing and planting crop varieties that are resistant to specific diseases and pests. 6. Monitoring and early detection, regular scouting, regularly inspecting crops for signs of pests or diseases. Use of monitoring tools, employing tools like pheromone traps or digital technologies for early detection. 7. Information and education, farmer training, providing education and training on IDPM practices. Extension services, offering support and information through agricultural extension services. Quality considerations, certification, labeling, and accreditation for processes. 1. Quality considerations, product standards, adhering to quality standards for processing agricultural products. Consistency, maintaining consistent product quality and characteristics. 2. Certification, organic certification, meeting requirements for organic production and processing standards. Quality certification, obtaining certifications such as ISO, International Organization for Standardization, for Quality Management. 3. Labeling, accurate labeling, providing accurate information on product labels, including ingredients, nutritional information, and certifications. Country of origin labeling, complying with regulations regarding the labeling of the country of origin. 4. Accreditation, accreditation bodies, seeking accreditation from recognized bodies to validate compliance with industry standards. Regulatory compliance, ensuring adherence to government regulations related to food processing. Marketing and exports. 1. Market research, understanding consumer trends, identifying consumer preferences and market trends. Competitor analysis, analyzing competitors and market dynamics. 2. Product differentiation, unique selling proposition, USP, highlighting unique qualities or features that set products apart. Brand building, developing a strong brand identity. 3. Export requirements, compliance with export regulations, meeting regulatory requirements for exporting agricultural products. Phytosanitary standards, ensuring adherence to phytosanitary standards for plant products. 4. Quality control, supply chain management, implementing quality control measures throughout the supply chain. Traceability, establishing systems for tracing the origin and processing of products. 5. Distribution channels, effective distribution networks, establishing efficient distribution channels to reach target markets. E-commerce platforms, utilizing online platforms for marketing and sales. 6. Promotion and marketing strategies, digital marketing, leveraging digital platforms for marketing. Promotional campaigns, implementing targeted promotional campaigns. 7. Export documentation, export licensing, obtaining necessary licenses for exporting. Customs documentation, preparing accurate customs documentation for export. 8. Sustainability and corporate social responsibility, CSR. Environmental sustainability, emphasizing sustainable practices in production and processing. CSR initiatives, engaging in social responsibility initiatives to enhance the brand image. Integrated disease and pest management, along with a focus on quality, certification, labeling, accreditation, and effective marketing strategies, contribute to the overall success and sustainability of agricultural processing operations, both in domestic and export markets. Compliance with industry standards and regulations is essential for building consumer trust and ensuring market access. Rain-fed agriculture, introduction, types, history of rain-fed agriculture, and watershed in India. Rain-fed agriculture, introduction, types, history, and watershed in India. Introduction. Rain-fed agriculture refers to agricultural practices that rely predominantly on rainfall for water supply rather than irrigation. It is a significant component of global agriculture, supporting the livelihoods of millions of farmers. Rain-fed areas are characterized by seasonal variability in rainfall, and crops in these regions are entirely dependent on the amount and timing of rainfall for their growth. Types of rain-fed agriculture. 1. Dryland farming, arid regions, agriculture in arid and semi-arid regions where water scarcity is a significant challenge. Drought-prone areas, regions susceptible to periodic droughts. 2. Moisture-limited farming, moderate rainfall areas, regions with moderate rainfall where water availability is a limiting factor. Varying moisture conditions, agriculture is dependent on the variability in moisture availability. 3. Humid rain-fed agriculture, high rainfall regions, agriculture in regions with ample rainfall. Seasonal variability, still subject to seasonal variations in precipitation. History of rain-fed agriculture. Ancient practices, rain-fed agriculture has a long history and was the predominant form of agriculture in many ancient civilizations. Traditional techniques. Farmers developed traditional techniques to cope with varying rainfall patterns, including crop diversification, soil conservation, and water harvesting. Community-based approaches. Many traditional rain-fed agriculture practices were community-based, with shared water management systems and collective decision-making. Watershed in India. Definition. A watershed is an area of land where all the water that falls or drains into it flows to a common point, typically a river or lake. Importance in rain-fed agriculture. Water management. Watershed management is crucial for optimizing water resources in rain-fed areas. Soil conservation. Prevents soil erosion and enhances soil fertility. Drought mitigation. Watershed development can mitigate the impact of droughts by improving water retention in the soil. Watershed development programs in India. Integrated Watershed Management Program, IWMP, launched by the Government of India to address land and water degradation in rain-fed areas. National Watershed Development Project for Rain-fed Areas, NWDPI, a centrally sponsored scheme focusing on rain-fed areas to enhance soil and water conservation. Components of watershed management: soil and water conservation structures, building check dams, contour bunding, and gully plugging. Afforestation and agroforestry, planting trees to improve water retention and prevent soil erosion. Livelihood diversification, promoting alternative livelihoods to reduce dependence solely on agriculture. Challenges and future prospects: climate change impact, changing rainfall patterns, and increased climate variability pose challenges for rain-fed agriculture. Technological interventions: adoption of climate-resilient crop varieties and sustainable agricultural practices. Community participation, involving local communities in decision-making for sustainable watershed management. Conclusion. Rain-fed agriculture plays a crucial role in global food production, particularly in regions where irrigation is limited. Effective watershed management is essential for sustaining rain-fed agriculture, ensuring water availability, and enhancing the resilience of farming communities. Historical practices and modern interventions contribute to the adaptation of rain-fed agriculture to the challenges posed by climate variability. Problems and prospects of rain-fed agriculture in India. Problems and prospects of rain-fed agriculture in India. Problems. 1. Climate variability, erratic rainfall, unpredictable and uneven distribution of rainfall affects crop growth and yields. Droughts and floods, frequent occurrences of droughts and occasional floods pose significant challenges. 2. Water scarcity, limited irrigation facilities, many rain-fed regions lack proper irrigation infrastructure, making crops highly dependent on rainfall. Groundwater depletion, over-extraction of groundwater in some areas exacerbates water scarcity. 3. Land degradation, soil erosion, vulnerability to soil erosion due to heavy rainfall and lack of soil conservation measures. Nutrient depletion, continuous cropping without proper nutrient management leads to soil fertility decline. 4. Low productivity, limited crop diversity, dependence on a few rain-fed crops may limit income opportunities. Subsistence farming, many rain-fed farmers engage in subsistence farming, limiting their market access and income potential. 5. Technological gap. Limited technology adoption, lack of access to modern agricultural technologies and practices. Information dissemination, challenges in reaching farmers with information on improved farming practices. 6. Socioeconomic issues, poverty and vulnerability, rain-fed farming communities often face poverty and economic vulnerability. Rural migration, limited opportunities lead to rural-urban migration. 7. Land tenure issues. Fragmentation, small and fragmented land holdings hinder efficient and sustainable farming practices. Land use changes, unsustainable land use changes can contribute to environmental degradation. 8. Policy constraints, insufficient support, limited policy support and financial resources for rain-fed agriculture. Risk mitigation, inadequate insurance coverage for crop losses due to climate-related events. Prospects. 1. Watershed management, integrated approaches, implementing holistic watershed management programs to conserve water, prevent soil erosion, and improve water use efficiency. Community participation, involving local communities in decision-making for sustainable watershed management. 2. Climate-resilient agriculture, drought-tolerant crops, developing and promoting drought-tolerant crop varieties. Precision farming, using technology for precise resource management based on climatic conditions. 3. Technology adoption, digital agriculture, harnessing digital technologies for weather forecasting, precision agriculture, and market access. Drip irrigation, promoting water-efficient irrigation methods. 4. Crop diversification, promoting agroforestry, introducing tree crops to diversify income sources and improve soil health. Intercropping and mixed farming, enhancing crop diversity for improved resilience. 5. Capacity building. Farmer training, providing training on modern agricultural practices, water conservation, and sustainable farming techniques. Access to information, ensuring farmers have access to timely and relevant information. 6. Market access, value addition, encouraging processing and value addition to agricultural produce. Market linkages, facilitating direct market linkages to improve farmers' income. 7. Policy support, incentives, providing financial incentives and subsidies for rain-fed agriculture. Insurance schemes, expanding crop insurance coverage to mitigate risks for rain-fed farmers. 8. Research and innovation, adaptive research, focusing on region-specific research to address challenges related to rainfall patterns. Technology transfer, bridging the gap between research institutions and farmers for effective technology transfer. 9. Sustainable practices, organic farming, encouraging organic and sustainable farming practices. Conservation agriculture, promoting minimal tillage and soil conservation practices. 10. Community development, livelihood diversification, supporting alternative livelihoods to reduce dependence solely on agriculture. Social infrastructure, investing in rural infrastructure, education, and healthcare. Addressing the problems and capitalizing on the prospects of rain-fed agriculture in India requires a comprehensive and integrated approach involving policymakers, researchers, extension services, and local communities. Sustainable agricultural practices, coupled with technological advancements and supportive policies, can contribute to the resilience and prosperity of rain-fed farming systems. Use soil and climatic conditions prevalent in rain-fed areas. Soil and climatic conditions prevalent in rain-fed areas. Soil conditions. 1. Variability, heterogeneous soils. Rain-fed areas often have diverse soil types, leading to variations in fertility and water holding capacity. Texture differences. Soils may range from sandy to loamy to clayey within the same region. 2. Low organic matter, limited decomposition. The absence of irrigation and less water availability can result in slower organic matter decomposition, leading to lower soil organic content. Risk of erosion. Low organic matter contributes to increased vulnerability to soil erosion. 3. Nutrient deficiency, leaching. Nutrients are prone to leaching due to heavy rainfall, leading to nutrient deficiencies. Acidic soils. Some rain-fed areas may have acidic soils, affecting nutrient availability. 4. Water holding capacity, limited water retention. Sandy soils prevalent in some rain-fed regions have lower water retention capacity, making crops susceptible to moisture stress. Improving water holding capacity, practices like mulching and organic matter addition can enhance water retention. 5. Erosion risk, slope erosion. Rain-fed areas with slopes are prone to erosion, especially during intense rainfall events. Soil conservation measures, implementing measures like contour plowing and bunding to prevent erosion. 6. Drought-prone areas, water stress. Rain-fed areas often experience water stress, leading to challenges in sustaining crop growth. Drought-resistant crops. Adoption of drought-resistant crop varieties is crucial. Climatic conditions. 1. Erratic rainfall, uneven distribution. Rainfall is often unevenly distributed, impacting crop growth and yields. Delayed or early monsoons, variability in monsoon onset and withdrawal affects the planting and harvesting seasons. 2. High temperature variability, temperature extremes. Rain-fed areas may experience temperature fluctuations, with periods of both high temperatures and cold spells. Impact on crop growth, extreme temperatures can affect crop development and yield. 3. Seasonal changes, distinct seasons. Rain-fed regions may have distinct seasons, such as a monsoon season followed by a dry period. Crop planning challenges. Farmers need to plan cropping patterns based on the available water during different seasons. 4. Limited growing period, short growing season. Some rain-fed areas have a limited window for crop cultivation due to seasonal constraints. Early and late crops. Farmers need to choose crops that match the available growing period. 5. Waterlogging and flooding. Flooding risks. Intense rainfall can lead to waterlogging and flooding in low-lying areas. Impact on crops. Floods can damage crops and affect soil structure. 6. Cyclonic activities. Coastal areas. Rain-fed coastal regions are prone to cyclones, bringing heavy rainfall and wind damage. Infrastructure vulnerability. Cyclones can damage agricultural infrastructure and disrupt farming activities. 7. Hailstorms and extreme weather events. Crop damage. Hailstorms and extreme weather events can cause significant damage to crops. Risk mitigation. Implementing protective measures, such as crop insurance, to mitigate risks. Understanding the soil and climatic conditions prevalent in rain-fed areas is essential for developing sustainable agricultural practices. Implementing soil conservation measures, adopting climate-resilient crop varieties, and employing water management strategies are crucial for enhancing productivity and resilience in rain-fed agriculture. Localized and region-specific approaches are often necessary to address the unique challenges of each rain-fed area. Use soil and water conservation techniques, drought types. Soil and water conservation techniques. 1. Contour plowing. Description: plowing along the contour lines of the land to reduce soil erosion. Benefits: helps in slowing down water runoff, promoting water infiltration, and preventing soil loss. 2. Terracing. Description: building step-like structures on slopes to create flat surfaces for cultivation. Benefits: reduces soil erosion by slowing down water runoff, conserves soil moisture, and provides stable areas for crops. 3. Cover cropping. Description: planting cover crops during the off-season to protect and improve soil. Benefits: prevents soil erosion, adds organic matter, and enhances soil fertility. 4. Mulching. Description: covering the soil surface with organic or inorganic materials. Benefits: reduces soil erosion, conserves soil moisture, moderates soil temperature, and suppresses weed growth. 5. Agroforestry. Description: integrating trees and shrubs with crops to create a more sustainable and resilient farming system. Benefits: helps in soil conservation, provides windbreaks, enhances biodiversity, and improves water retention. 6. Rainwater harvesting. Description: collecting and storing rainwater for agricultural use. Benefits: mitigates water scarcity, recharges groundwater, and provides a supplementary source of irrigation. 7. Check dams. Description: building small dams across ephemeral streams to check water flow and promote sedimentation. Benefits: reduces downstream erosion, traps sediment, and enhances water availability. 8. Gully plugging. Description: blocking or filling gullies formed by water erosion. Benefits: prevents further gully erosion, conserves soil, and improves water retention. 9. Crop rotation and diversification. Description: alternate